Welcome. The topic is the past, present, future of time in physics. That's a very broad and sweeping topic and couldn't be covered in one presentation. So, this is part one, where we will look at the history of time in physics. Part one happens to be a redo of a talk that I gave to the CMPS back in 2014, and is also talk number 29 in my Nick of Time YouTube channel, giving a series of 33 talks on time and physics. So we're going to look at the history of time in physics through the millennia. And we're not going to look at those debates from the philosophers about time, as those debates were much too vague and could not come up with a concrete enough construct to use in a physics model. So we're not only going to talk about the history of time in physics, but the perspective will be from a mainstream physicist, namely Professor Lee Smolin, who also is really giving the consensus opinion about the history of time in physics. And we'll end up with a high-level conceptual discussion of special relativity and general relativity's view of time. And then in part two, where we talk about the present of time in physics, we will delve into that topic on relativity a lot more deeply, including the evolution from 19th century physics to Einstein's paper in 1905. And that should be extremely insightful and give you much greater understanding of relativity. Since much of this talk will be based on Professor Lee Smolin's ideas, we need to know more about him, including his biases, etc. He's a highly respected mainstream physics professor in academia who loves relativity. In addition, he's also a critical thinker. He wrote a book criticizing string theory as being too much math fantasy and not enough hard physics. He also wrote the book Time Reborn, which is an excellent book that I recommend to all, and it's the basis for this first talk. We'll start off with a summary of that book. The main thesis is that the concept of time has been slowly removed from physics. Einstein claimed that the distinction between past, present, and future is only a stubbornly persistent illusion. And that thought is certainly contained in both special and general relativity. So this removal of time from physics, the peak to date anyways, is in relativity. So Lee recommends that time needs to be put back into physics, and especially for cosmology and quantum gravity. Lee starts off by describing ancient intuitive views. Now, if one's standing on the Earth, one has no sense that the Earth is rotating about its axis or orbiting around the Sun, so the intuitive concept is the Earth is at rest, and that people are at rest, except when they're walking and moving with respect to the Earth's surface. So their view was that not only common everyday humans, but the scientists and physicists of the time, the concept was that the sun, the moon, the planets, the stars all moved with respect to the stationary Earth. Also, and this is quite important, that the passage of time was defined in terms of those motions or those astronomical processes. The day was thought to be the time, naively thought to be the time, that the sun makes a full rotation around the Earth, whereas in reality, uh, it's really that the Earth is making one rotation about its axis. And the week is 7 rotations about the Earth's axis, and an hour is 1/24th of the time it takes for the Earth to rotate once around its axis. And even the month is approximately the corresponds to the moon going through its various phases. In addition, the ancients thought of there being 2 separate worlds. The celestial realm was unchanging and had perfect repeating patterns, versus the realm of the imperfect, chaotic Earth. They consider them 2 quite different, separate realms. Here's a picture of that ancient view with the Earth at the center and all the celestial bodies going in perfect circles around the Earth, including the moon, the sun, all the planets, and all the stars. And to the degree that the precision of their observation of the time, it worked out pretty well. So that's the picture of Ptolemaic astronomy. And Lee makes the point regarding that and geocentrism is there's a lesson here, which is that neither mathematical beauty nor agreement with experiment can guarantee that the ideas a theory is based on bear the slightest relation to reality. I would contend that regarding relativity, uh, that lesson was completely ignored by Lee, as we'll discuss later on. So the Ptolemaic view continued to evolve, like science is always evolving. Sometimes it goes down the wrong path even, but it's always changing. So the view was that the heavenly bodies always moved in perfect circles around the Earth. But then they found that there were some retrograde motion, so that nice simple picture became more complex as they had to add 55 circles to take into account retrograde motion. But they were still stuck on circles because that was considered the perfect symmetric shape. Then Tycho Brahe came along and made another step forward. He said that the planets travel around the sun, and that yielded a much simpler picture. But because his belief in the Earth-centered view was still strong, he couldn't make that next step. So he said that, well, the sun still moves around the Earth. He assigned Kepler to analyze the orbit of Mars, and Kepler, doing careful work, saw that that orbit was really an elliptical orbit and not a circular orbit. And he made a great jump and change in paradigm and saw that the Earth was also moving around the sun. Now everything, all the planets were moving around the sun. So that really was quite a major change in astronomy, a paradigm change. But it also was a great change in terms of time, in terms of the underlying model of time, because in the geocentric view, a day was the sun making one revolution around the Earth, but the true physics was that the underlying motion, the underlying process of the day was the Earth making one revolution about its axis. Okay, having covered a couple of thousand years of physics, we come to Galileo, and he was the first one to discover that the motion of all thrown objects follows a simple type of math curve, a simple geometric object. The parabola, the math definition is that it's the loci of points that are equidistant from a specific point and a specific line. And the equation is simply y equals x squared. It's a static equation describing the entire parabola at once, and there's no t for time in there. So at least scientists now are beginning to apply and see patterns in what happens in the realm of the Earth, not just celestial objects. So, back in the days of the Ptolemaic picture, we had everything orbiting in circles, and then we advanced to seeing the orbits as ellipses, and now we have Galileo introducing a parabola to describe thrown objects. But all of those pictures are static in the sense that they show the entire motion or process as all at once. So Lee's point is that physics was really treating a dynamic process as a static math object, where these geometric objects give a static picture of the whole phenomenon at once, and the same for equations. So Lee went on to say that math is timeless, pure thought, unchanging, and there's no place for observation or measurement. For instance, for the parabola was discovered purely from math manipulations, and it was only after the fact that it was applied to thrown objects. But if you're just thinking in terms of math and can use any of the many math manipulation, that can lead to fantasies because you're not being tied to the physicality of the real world. And regarding time, this treatment of dynamic processes as static math objects was really the first step to spatialization and geometrization of time. Spatialization means treating time as though it were another spatial dimension. And that, that tendency was fully realized in relativity. Moving ahead a couple of centuries, we come to Newton. And his key constructs for time are absolute time and absolute predetermination. Regarding the latter, Newton said that, well, given the initial position of all particles and their initial velocity and the forces that exists, then everything is predetermined. So that view pictures everything really as a static whole. The universe had become timeless in Newton's model, an unchanging solution. Time was really replaced by computation. And again, well, these are Lee's views. Basically, everyone I've read about this period says the same thing. Regarding absolute time, the model really pictures like there's some universal clock, maybe even outside the universe, that progresses at a consistent pace throughout the universe. It's independent of any observer and separate from absolute space. We jump forward 150 years or so to special relativity, which gets rid of time in physics in many ways. First of all, it replaces absolute time with relative to the observer time. And if you read the 1905 paper, it's very interesting that there's no attempt by Einstein to say, oh, here's the reasons with absolute time, and here's the benefits of going to relative to the observer time. And that is mostly true in terms of the physics community. You might assume that such a dramatic change in paradigm would be at least debated, or even if everyone instantly agreed, that they would enumerate all of the benefits of this change. But no, some peripheral comments, of course, but in general, no. We would just accept it. Furthermore, Einstein redefines time in terms of the speed of light and assumes that the speed of light is constant for all observers in all inertial frames for both the speed of light approaching those observers and the speed of light receding from all those observers. And this is implemented into special relativity in the following way. If you're going to use special relativity in an inertial frame, you have to synchronize your clocks using Einsteinian synchronization, which goes like this. You send a signal from clock A to clock B, and that signal is sent back to clock A. When it gets to A notes the total time for that clock, for that round trip of light. It then divides that total time in half by assuming it takes the same amount of time to go from A to B as it does to have light go from B to A, regardless of the motion of that inertial frame. So if you do that, if you synchronize your clocks that way, regardless of physical reality, then you're guaranteed to measure the speed of light as being a constant c, whether that light wave is going away from A towards B or towards A from B. So the net result is that time equals the length of the path that it's traveled divided by c. Time is defined in terms of the speed of light and assumes that the speed of light is constant for all inertial frames. The mathematician Hermann Minkowski, who had taught Einstein math in the past, showed that Einstein's special relativity equations were equivalent to Minkowski space-time diagrams. In these diagrams, we'll see that time can morph into space, and space can morph into time. So one selects a particular inertial frame and has the black axes representing the time and x direction in space. But for another frame that's moving with respect to the black frame, let's call it the blue frame, there's a different view of what's time and what's space. Those axes are rotated by the angle alpha shown here, which is a function of the relative velocity between the blue frame and the black frame. So time, which is multiplied by the speed of light to have it measured in terms of meters, just like the X frame. Time in one frame becomes space in another, and space in one frame becomes time in another. So if we shift and have the blue axis, now called the stationary frame, and the black axis is moving, of course, the same speed relative to the z-axis, then we have a mirror image of this picture showing how time of one morphs into the space of another and vice versa. Still another way that special relativity gets rid of time in physics is the construct of relative simultaneity. Each inertial frame or inertial observer has their own idiosyncratic view of what's simultaneous. For example, for some event X that A observes as being simultaneous with his present state, there will be another observer who sees X as simultaneous with an event in A's future, and a third observer who sees X as simultaneous with an event in A's past. Hence, in special relativity, there's no global past, present, future. Each observer has their own construct of past, present, future, and of what's simultaneous. Sometimes the picture helps. So we'll look at this admittedly crude diagram, and we have in special relativity, Maria's the observer, so her time axis is perfectly vertical and her space axis is perfectly horizontal. And she's at point A, which is zero time and zero distance on the horizontal axis. Now, event X happens on that horizontal axis, so Marie sees event X, as simultaneous with her current present. However, we have Freddie. Freddie is moving at some velocity with respect to Maria, so his time and space axes are rotated with respect to Maria's in special relativity. And B, Freddie is at event or location B in this space-time diagram. And Freddie sees X as being simultaneous with some point that's in Maria's future. So they have totally disagreements of is X in the present or is X in the future, even within Maria's diagram. And of course, we could have another observer who sees event X as being in Maria's past. So everyone has a different view of past, present, and future. Lee continues, special relativity and general relativity gets rid of time. In the relativistic universe, it's like a timeless unity. The flow of time is an illusion. Relativity's reality is there's no global past, present, or future. All there is a four-dimensional space-time, where time is not separate from space. And that four-dimensional space-time is like a frozen block of ice. In special relativity's construct of space-time, in Einstein's words, space and time are subjective ways of dividing up a four-dimensional reality. In relativity, the universe is a mathematical, geometric object, called by all the block universe view. General relativity is even more timeless than special relativity. It confirms the block universe view, and the construct of past, present, future only has local, observer-dependent meaning in the same sense as the terms here, left, right, and near describe location in space relative to an observer. General relativity is about the geometry of four-dimensional space-time, where the key construct is its 4D metric. And most interesting, and I think quite important, is that Einstein himself was distressed that the now, the present, and the sense of past and future was absent from physics theory, and thought that this was a shortcoming, but, in the context of relativity, saw no possible resolution. As a quick aside, I'll note that Lee brings out that quantum mechanics is also timeless and compatible with special relativity's relative simultaneity. However, the alternatives to quantum mechanics, such as the hidden variable theories of de Broglie and Bohm and Vigier, require absolute simultaneity. I had not known that before reading Lee's book, but I'd always had a preference for the alternative theories. They seem to be inherently more physical. Okay, on the theme of time has been removed from physics, or at least the essential properties of time, the past, present, future, simultaneity. We started off by saying there was a freezing of motion when it was transformed into a physics graph or into a static physics formula. This abstraction, with just a view of the math view, gave the picture of the entire process, and no hint about its evolving through time. Next was the Newtonian view, which introduced predetermination, which seemed to be like a precursor to the block universe view. Next we had relativity introducing relative simultaneity, which meant that there's no global past, present, or future. It's all observer dependent. And finally there was the four-dimensional space-time block universe of general relativity, where space and time were welded together. Just to be clear, in case someone is thinking, I've been studying special relativity, and a lot of its equations include T. Yes, that's true. T standing for proper time or observed time. But the point is that these points on this chart refer to special relativity's model, and in that model, some of the key properties of what we think about as being inherent in time, like the past, present, future, or simultaneity, have been removed from that special relativity model. Okay, we just summarized Lee's main thesis, namely that the properties of time have been removed from physics, and he considers that a problem. And further, the ultimate example of the essential properties of time being removed from physics is relativity. However, he goes on to say that he prefers relative time to absolute time. And he references Leibniz, who had his principle of sufficient reason. Leibniz said for questions like, why is the universe like this, there must be a rational answer. There must be a rational reason. So he looks at absolute time, and he gives the rhetorical question and answer, would it matter if the universe started 10 minutes later than it did? And Leibniz says, no. Therefore, time is not absolute. And Lee says, I accept Leibniz's reasoning. I would just comment that I think Lee was a little too quick and perhaps too inclined to accept a rationale for accepting the rationale over the absolute. Regarding that second bullet, I think it might prove that when you started the universe with time, might be relative. But using Newtonian thinking, whether you start the universe at x or x plus 10 minutes, if you use the same initial parameters, initial conditions, then you could have absolute time in both cases, just absolute with respect to whenever you started the universe. Just a thought. Since we're talking about absolute versus relative, we'll, as an aside, talk about motion. Lee makes the point, if motion is inherently relative, that does present a problem, another problem with relative, in that you can't assign any specific physical cause to that motion. And he further makes the point that geocentrism, which he dismisses as not good physics, rather Rube Goldberg-like model, it can only be justified based on relative motion. If all motion is relative, then you can take a Ptolemaic view of the world, even though the model is extraordinarily complex, and you have to add 55 adjustments for retrograde motion and have a rather convoluted explanation of the physics of what's going on and driving the motion of everything around the Earth. So there he concedes to strong arguments against physics viewing all motion as relative. In addition, I'll add my own view that I think there are good arguments that rotational motion and acceleration are absolute, because when you start the acceleration or rotational motion, you're introducing forces that weren't there before. So I extrapolate from that and say that when you accelerate from x to x plus 50, you're going from one absolute state to another absolute state of constant motion. Now we come to Lee's conclusion, and we'll also look at the challenge for Lee about that conclusion. Lee concludes that time has been removed from physics, as we've seen. But Lee concludes, but at least for certain areas, cosmology, quantum gravity, hidden variable versions of quantum mechanics, needs time. Physics needs time. But that conclusion presents a problem for Lee, because his belief system includes special relativity and general relativity, which are timeless. Lee's solution continues. He says we have to give up relative simultaneity and adopt a preferred global time and determine, at least for cosmology, the cosmological preferred state. And Lee further says, the fact that this contradicts the triumph of Einstein over the ether is a psychological barrier to taking the arguments for the reality of time seriously. And finally, he says, on a cosmological scale, preferred frame is valid, but on a smaller scale, relativity prevails. We'll now take a little bit of a deeper look at Lee's solution. He says, even on a cosmological scale, the preferred frame is determined by the actual distribution of matter and gravitational radiation, something that I would agree with. So it's not a throwback to Newton's absolute time. Yes, I'm in favor of absolute time versus relative time, but I do not want to go back to Newton's version of absolute time. So Lee continues, however, the day is saved by a new theory, shape dynamics, which gives the same results as general relativity. Now I'll give a few points to compare general relativity with shape dynamics. They both have limitations, but they're kind of complementary. In general relativity, simultaneity has meaning if two events are close, but as separation increases, the meaning of simultaneity decreases. However, in shape dynamics, comparing absolute size has meaning if two objects are physically close, but as separation increases, the meaning of absolute size decreases. So Lee keeps general relativity, but when Lee needs time to be meaningful, Lee just switches to shape dynamics. So Lee's solution, which we've just discussed, seems similar to what I've encountered many times. Namely, a relativist will claim that relativity is gospel, but he sees a problem in relativity and does an ad hoc fix to relativity. And then his view is relativity is correct, but the rest of the world is not understanding relativity correctly. They should be moving over to my modified version of relativity. Anyway, many relativists see the same problems in relativity, and there are quite a few different ones, and usually the relativists will see one out of many and to focus on that one. They say the same problems in relativity that dissidents have articulated, but the two groups have different solutions. The relativists tend to patch with an ad hoc fix, whereas the dissidents/critical thinkers are inclined to take relativity to the landfill and come up with a totally different approach. So Lee's approach it strikes me as Rube Goldberg-like, by using relativity for some areas of physics, but when the properties of time are really needed, switching over to another theory. I just have the feeling that there must be a smoother solution. Okay, we'll wrap up part one with a summary of some key concepts that will be very important to understanding part two and part three. First, time has been slowly removed from physics, culminating in total removal from special and general relativity. In a few charts back, we gave some more detail to that, giving some specific examples. But despite this removal, Lee notes that certain areas of physics need time. For example, cosmology. But both Lee and Einstein and others can't find a way to put the essence of time back into relativity. And the final point is a general point. It's a quote from Lee saying, "Neither mathematical beauty nor agreement with experiment can guarantee that the ideas a theory is based on bear the slightest relation to reality." An important point for this series of talks and for all of physics. And it needs to be remembered if you want to be a critical thinker in physics. Before I go, I'll give you a quick preview of part two. It's a deep analysis of how special relativity evolved from Lorentz ether theory, yielding critical insights into relativity. And we'll do this through the lens of the construct of time that we talked about in part one. If you're a critical thinker, your view of special relativity will be transformed forever.